All right, so today we're going to be talking about high frequency transistor models. So let's start by looking at a BJT. And how I'm going to approach this is I'm going to give you guys the models first, and then we're going to talk about where all of these additional components are coming from and what phenomena is giving rise to them. Okay. So for our BJT, here is our base terminal. And we know that between our base and our emitter, we should have some resistance R pi. And we typically call this voltage drop right here VBE. I'm going to give myself plenty of room. Here's where we're going to have our emitter terminal. Here's GM VBE in parallel with R naught. And then over here is our collector terminal, right? So this is this is what we know as our BJT small signal model. In just a moment, I'm going to dim the lights a little bit. And to this model, we are going to add a couple of capacitance. Okay. So the first capacitance that I'm going to add is going to be between the base and the emitter. We're going to call this capacitance C pi. I'm going to add a capacitance between the base and the collector, which we are going to call C mu. And lastly, we are going to add a capacitance between the collector and explicitly ground, which I'm going to call CS. So all of these capacitances are representing different charge storage mechanisms that we kind of glossed over when we talked about the BJT's operational physics. And what I mean by that specifically is we paid attention to charge and all of that kind of stuff, but we just assumed that charge was able to instantly move from one place to another, and we know that that's not true. It takes time for charge to accumulate and all that kind of stuff. And that's what all these capacitances represent. So I'm going to draw a picture of a BJT operating in the forward active mode, and we're going to talk about where these capacitances manifest. Okay. So I'm going to put my large signal emitter terminal over here on the right. I am vastly exaggerating the size of the base here, just to be really clear, because it should be the smallest region. And then over here is my collector. So just as a reminder, our emitter is the most heavily doped region. Our collector, if this will write a capital C, there we go, is the most lightly doped. And then our base is medium doping. And obviously this is going to be an NPN transistor based on the doping concentrations that I've given. We want this device to be in the forward active mode because that's when the mode of operation that we use for amplification. So that means that our base emitter voltage needs to be positive. So VBE here has to be greater than 0. And our base collector junction needs to be reverse biased. So VCB here be less than 0. All right, so let's look at our carrier concentrations first. Or actually, first let's define our depletion region widths because that's going to play a big role in things here. So because my base emitter junction is an N++, P+ junction, and it is forward biased, we are going to have a depletion region, but it is going to be rather small, right? So we're going to have it extend into the N region by some amount, and it should extend into the base region by a larger amount because of lightly doping on the base side as compared to the emitter side. And then we're also going to have a depletion region for our collector base junction. So something into this. And so what we should see is that we have some positive charge, which I'm going to call QBEP, stored here. Some negative charge, which I'm going to call QBEN, stored in this part of the depletion region. QCBN will be stored here. And QCBP will be stored here, right? So we have two different PN junctions, each with accumulated charge on either side of their depletion region. And so this is where two of our capacitances wind up coming from. We're going to wind up lumping these together and all that kind of stuff here in a moment. But I also want to look at what's going on with our carriers diffusing across this junction. So if memory serves me correctly, earlier in 335, I used blue for electrons and red for holes, I believe. So I'm going to try to be consistent and do that here. So if we look explicitly at carrier concentrations, let's say that our electron concentration is up here for this region, and then let's put it roughly here for the base region, and then here for the collector region. And then my holes should look something like this. So when we're looking at the base emitter junction in particular, we know that charge carriers are diffusing across that forward bias junction, and that the width of that base is very small so as to not allow too much recombination. So this is going to be drawn as if recombination is occurring, so I don't want to stretch this thing too far. But what I'm trying to illustrate is diffusion charge is being stored as well. We might have something like this, where we have some charge here. This is negative diffusion capacitance charge being stored over here. And similarly, holes should be able to diffuse across the base emitter junction. So we should see something like this. I wish I could draw a curve to save my life. This will be UDP. Right. So we have depletion capacitances for both of our junction, because there is going to be depletion region, even if it is still for bias and reverse bias. And then we have diffusion capacitance explicitly for the base emitter junction, because we have minority carrier injection into the other region, right? So let's start by looking at this diffusion capacitance. So our charge QDN is going to be given by a coefficient tau sub f times whatever our collector current is, where tau sub f is the forward base transit time and represents the average amount of time a charge carrier spends crossing the base. So recall, again, that our base is very, very short, right? Or very, very small in width, intentionally. We don't want a very wide base, because that will increase the probability of recombination to occur, which would mean that our base would have to supply more hole currents, and we just wouldn't have an as efficient of a system. Okay? So because the base is very small in width, the average amount of time it takes for a charge carrier to cross the base is incredibly small, typically on the order of 1 to 100 picoseconds, so 10 to the minus 12 to 10 to the minus 10 seconds. Okay, very, very, very small amount of time. Our collector current is exponentially related to our base emitter voltage. So that means that the charge QDN also has to depend on our base emitter voltage. So we can define a capacitance CDE that is simply the change in QDN with respect to the change in VBE. Since our forward base transit time is a constant, this is simply the change in IC with respect to VBE. What's the change in IC with respect to VBE? Say it louder, please, Hannah. The transconductance, exactly. That is literally how transconductance is defined. So that's nothing more than tau F times GM, or tau F IC over VT. So we also have a base emitter junction capacitance due to the stored charge in the depletion region. Since the base emitter junction is forward biased, CJE, which is what we're going to call this. So CJE is the junction capacitance. Since it's forward biased, CJE will be larger than the unbiased value, right? So if our depletion region is smaller in width, the distance separating the plates of our parallel plate capacitor is smaller, which means the capacitance goes up. So we should have CJE is equal to CJE naught, our unbiased junction capacitance, over 1 plus VEB over V naught E. So that V naught E is the built-in voltage for that junction to the mth power, depending on the grading coefficient, whether it's a step junction or a linearly graded junction. And this is typically accepted to be approximately twice CJE naught under forward bias. Since these two capacitances both occur across the base emitter junction, they are effectively connected in parallel. And so our capacitance C pi in our high frequency model is just the combination of these two phenomena. So we have our diffusion capacitance across our emitter as well as our junction capacitance. So that's where one of these guys comes from. We have depletion capacitance between the base and the collector terminals, right? So C mu is just CJC naught, where that is the depletion capacitance across the base collector junction divided by the voltage 1 plus VCB over V naught C to the nth power. And now the only capacitance that we have left to explain where it comes from, looking at our model, is this capacitance CCS, right? So just to be clear here, this C pi depends on depletion capacitance and diffusion capacitance for the base emitter junction, which is why it's placed between the base and the emitter terminal. Yeah, that one. C mu is all about the depletion capacitance between the collector and base terminals, which is why the capacitance shows up between the collector and base terminals. And now we've got this guy CCS. So to understand what CCS is, it's effectively a parasitic, yes. Correct. So I draw the inequality sign the wrong direction? Yeah. Probably. Yep, no problem. It's definitely supposed to be reversed by whatever way that inequality is supposed to be. Yes. So that capacitance CCS is representative. I'm going to draw a picture over here to the right. So if we look at how a BJT is literally formed, this is the top of our substrate. This is the bottom of our substrate. So we have our N++ region here for our emitter terminal. We have our P+ region here for our base terminal. And then here, we have our N region for our collector terminal. Draw that as a capital C. And down here, we might have a P substrate, particularly if we are designing a, I don't remember the exact word, but effectively there is a complementary BJT technology, just like there's a complementary MOS technology that allows us to fabricate N-channel devices and P-channel devices on the same substrate. We can do literally the exact same thing with a BJT thing. So we would have a depletion capacitance between the collector and our substrate in an integrated circuit BJT. That depletion capacitance is this CCS. It's between the collector and the substrate. Okay. So it is the exact same mathematical relationship as we saw earlier. It's going to have a different built-in voltage than all of the other junctions because it's got a different doping profile than the other junctions and all that kind of stuff, but it behaves the exact same way. So it's just a third, less obvious example of a depletion region that we are going to see. So let's work a quick numerical example here where we want to calculate the values of C pi, C mu, and CCS, bless you, for a BJT operating at IC is equal to 1 milliamp. VBE is 0.775 volts. And VCB is equal to 2 volts. The BJT has the following parameters. So for the base emitter junction, we have CJE naught is 20 femtofarads. V naught E is 0.9 volts. And the grading coefficient is 1/3. For our base collector junction, we'll have CJC naught, 20 femtofarads. V naught E in this case will be 0.5 volts. And we have a grading coefficient of 1/3. And lastly, the collector substrate junction. We have CJS naught is once again 20 femtofarads. Our built-in voltage, excuse me, this should be V naught S, 0.4 volts. And our grading coefficient is 1/3. And the last piece of information that we need, and this is common to everything, is that tau F is 20 picoseconds. So from this information, our base emitter depletion capacitance is going to look like 20 femtofarads over 1 minus 0.775 over 0.9 to the 1/3 power, comes out to be 38.620 femtofarads, almost double, which is exactly what our simple approximation would be. CDE is going to be tau F IC over VT. So that is 20 times 10 to the minus 12 seconds times 1 milliamp over 26 millivolts. Looks like 769.231 femtofarads. And if we add these two guys together, we see that C pi comes out to be 807.850 femtofarad. C mu, pretty much the exact same equation as CJE. So we're going to have 20 femtofarads over 1 plus 2 volts over 0.5 volts to the 1/3, comes out to be 11.696 femtofarads. Let me ask you guys a quick question here just to make sure you're paying attention. Why do I have a minus sign in my CJE equation and a plus sign in my C mu equation for the voltage across the junction? Right. So typically speaking, we use a plus sign for reverse bias voltages, and we would use a minus sign for forward bias voltages with the understanding that we're expecting the capacitance to get smaller under reverse bias and larger under forward bias. So yes, absolutely correct. And lastly, CCS is 20 femtofarads over 1 plus, we'll sort this out in a second. So we know that this junction has a built-in voltage of 0.4 volts. What is the total bias voltage across this guy? How did you get there? So we're looking for VCS effectively, right? So we're looking for the voltage applied at the collector with respect to the substrate. So let's make an assumption here, which is usually true. Our substrate is at ground, an absolute ground for an integrated circuit. So what would the collector voltage be? It should be the highest point of electric potential in our circuit. So I would argue that it's going to be 2.775 volts. It's going to be the voltage drop across the collector base junction plus the voltage drop across the base emitter junction to give us the total voltage, that very highest point. So 2.775 over this 0.4 comes out to be 10.373 femtofarads. And so we can see from this that C pi is significantly greater than C mu is greater than CCS. That was true for this example, and it should be true for literally anything that we deal with, okay? So this relationship should be true for all BJTs in active operation. So it would be wonderful if this information were provided to us on a data sheet for a transistor. It is not. Gross, gross, gross. Okay. So let's talk about how we sort this stuff out in practice. Okay. So C mu and CCS, of course, the small ones that in the grand scheme of things are going to matter less than C pi, can be experimentally determined by measuring the capacitance seen between the base and collector or collector and substrate at the desired reverse bias voltage. So effectively, you literally just bias this thing with a large negative voltage that you expect it to operate under, and then measure the capacitances at that particular operating point, because it's going to change depending on what the operating point is. Yay for nonlinear circuit elements. Right? To figure out what's going on with C pi, we actually have to have an understanding of what's happening with beta. So previously, we have just used beta as a constant value, but beta actually changes with frequency as well. And we can observe that by looking at our circuit and measuring what beta should be. So beta represents the common emitter short circuit current gain of a transistor, right? So we defined beta as the ratio of the collector current to the base current. So if we use our model, so we are effectively going to inject some base current into our system. So this is our base terminal. Here's our emitter terminal. Now I'm just going to interpose my model in here. So here's R pi, VBE. C pi, which is what we're ultimately kind of looking for. C mu. GM VBE. Let's explicitly ground our emitter terminal. Here's R naught. Because our emitter is at ground, CCS will just be between the collector and the emitter. Here's our collector terminal. Here's our emitter terminal. Recall that this is a short circuit current gain, so we're going to short circuit the collector and emitter terminals. So let's call this node right here node X. And let's call this current IC. We're trying to find the relationship between IC and IB because that will be our gain. So we're applying KCL at X, right? Okay. So I have some current flowing in through that capacitor. I have a current of IC flowing in. So let me explain why explicitly I have a current of IC flowing in. CCS is grounded or shorted on both sides, right? So no current's going to flow through that impedance. R naught is shorted on both sides. So no current's going to flow through that impedance. So we have a current IC flowing in from the right, current flowing through the capacitor coming in from the left, and a GM VBE flowing out. Okay. So what's the voltage drop across my capacitor C mu? VBE. Absolutely. So the current flowing through my capacitor C mu should look like S C mu VBE. Right? Because voltage divided by impedance is going to give us current. Our impedance is 1 over S C mu. So V divided by 1 over S C mu looks like V times S C mu. Just Ohm's law using Laplacian math like we did in B24. Going to be doing that a lot for the next bit. Plus IC is equal to GM VBE. And so this could be rearranged to find that IC is GM minus S C mu times VBE. Okay. So now let's sort out what V pi is going to be, or VBE is going to be. Okay. So I would argue that our current IB sees a resistance R pi in parallel with the impedance of C pi in parallel with the impedance of C mu. Everybody okay with that? So VBE should be IB times R pi in parallel with 1 over S C pi in parallel with 1 over S C mu is going to look like IB divided by 1 over R pi plus SC pi plus S C mu. Putting these relationships together, beta is just the ratio of IC to IB is going to be GM minus SC mu divided by 1 over R pi plus SC pi plus SC mu. And we can approximate this when our conductance GM is greater than the conductance SC mu as GM R pi over 1 plus S C pi plus C mu times R pi, or beta naught, our low frequency value for beta, over 1 plus S C pi plus C mu times R pi. Yes. So you're saying, how did I get from here to here? Oh. Yeah. So yeah, so VBE is equal to IB over that means if I move the IB over here, I just wind up putting a VBE down here, and then when I do this guy over this guy, the VBEs cancel out. Yeah. Yeah. I just wanted to make sure that I fully thought. You guys are asking good algebra questions, and I take shitty notes. So. All right. So if I were to plot beta as a function of frequency, it would look something like this. So here's the magnitude of beta measured in decibels. Let's put here as beta naught. Let's do this in blue just for argument's sake. So we should see that we roll off at negative 20 decibels per decade because we very obviously only have a single pole based on our transfer function here. Down here is going to be 0 dB. All this omega B, and then this guy right here where it crosses 0 dB omega T. So omega B, which is just our pole frequency, is 1 over R pi C pi plus C. So that's where our -3 dB frequency where it's rolling off and all of that kind of good stuff. Nothing particularly wild or crazy about that. Omega T, let's talk about what that represents. So omega T represents the frequency at which beta is 1. Right? Because when we're at 0 decibels, that means we're at 1. Okay? So this is effectively what we would call the unity gain bandwidth of our transistor. Because our current gain, the ratio of our collector current to our base current, is at exactly 1 at this particular angular frequency. So we have omega T is, sorry, beta naught times omega B, just a gain bandwidth product here, effectively, is equal to GM over C pi plus C mu, which will be approximately GM over C pi, since we know that C pi is much, much greater than C mu. So effectively, if we can measure our unity gain bandwidth, and we know the transconductance at our particular operating point, we can back calculate what C pi is. That's the process for doing so. So transconductance obviously depends on our operating point. Beta as a function of frequency, that's definitely going to be in your data sheet. So we have enough information putting those two things together based on what our operating point is and how our transistor behaves as a function of frequency to know what all of our capacitance are. All right. So now let's talk about what's going on with MOSFETs. Yes. Nope. So yeah, so we're talking about, so that's a very good question, right? So if we were talking about our DC biasing and all of that kind of stuff, like literally all of our inputs are purely DC, right? So all of those capacitances look like, let me go back to our model here. All of those capacitance would look like open circuits, and we would literally just have the exact small signal model that we're used to dealing with at DC. So these are telling us how it's going to behave when we excite our circuit at high frequencies. However, I want to point out something here, and we're going to get into this a bit on Wednesday. The capacitance values that we're dealing with here are very high, right? Or excuse me, very, very small. Sorry, yeah. So the frequencies associated with those capacitors are then in turn very, very high. So getting a little bit ahead of myself, what we're going to see effectively is that every transistor amplifier that we've dealt with is going to look like a bandpass filter, where its low frequency response is dominated by the biasing capacitors. So the coupling capacitors and the bypass capacitors that we said looked like short circuits back in 335, and its high frequency response is going to be dependent on all of these internal capacitances. Now, what the limits are on those frequencies are dependent on what these capacitor values are. So everything that we learned about in 335, all of those single transistor amplifiers and its characteristic input resistance, output resistance, and voltage gain is what we call the transistor's behavior in the mid band. which is between the low frequency response and the high frequency response. And that is the region of the bandpass filter where the amplitude is effectively constant. What we're about to be looking at is what happens when we're below midband frequencies and what happens when we're above midband frequencies to make sure that things don't go too wonky. And largely speaking, in an open loop configuration, they won't. But in a closed loop configuration where effectively we have feedback, even if we're intending to apply a negative feedback at certain frequencies, that will turn into positive feedback. And so we have to look at our system stability as a whole to make sure that our gain goes down to incredibly small before we have our negative feedback turns into positive feedback so that we don't come up with an oscillator when we're trying to make an amplifier. So that's the context of literally everything we're doing for the rest of the quarter. So I don't know. Yeah, the best way that I can figure out to explain that just off the top of my head would effectively be to use either a Laplace transform or a Fourier transform to decompose that rectangular pulse into a sum of sinusoidal pulses, and then we can do frequency analysis on each of those harmonics to figure out what's going on. Because some of them are for sure going to be in the midband, but several are not. Right. Which that process could literally be true for anything we ever wanted to look at. By the way, we know, hopefully, at this point as electrical engineers, that damn near any signal can be decomposed into a sum of sinusoids and all that kind of jazz. And so then we could just look at it frequency by frequency and map what's happening. And that is literally the frequency response of the circuit. All right. MOSFET time. All right, so this model is arguably going to be gross. It's not going to be horrifyingly more gross than the BJT one. And again, this comes about because we've glossed over the fact that all of the capacitances that we dealt with specifically, or identified specifically when we were doing the MOSFET operational physics, we just assumed that charge can move instantaneously when we know that it cannot. So here's our model. Here's our gate terminal. Over which we have a voltage VGS. Here's GM VGS. If body effects are present, we'll have GMV, VBS, some resistance R naught. I'm going to put my source terminal down here, send this on like so, and put my drain terminal over here. And here's my body terminal, like so. So this is what our model would look like without any frequency dependence when we are including body effects, which we have largely ignored at this point. We are now going to have to include some gate source capacitance, CGS, some gate drain capacitance, CGD, some source body capacitance, CSB, and some drain body capacitance, CDB. For what it's worth, I much prefer the naming convention for the MOSFET capacitances because it literally explains what they are with their names. The gate source capacitance is between the gate and the source because we know that effectively the gate and the source form a parallel plate capacitor. That's how charge accumulates and we get strong inversion and all that kind of stuff. Shouldn't be any stretch of the imagination to understand why there would be a gate drain capacitance. A similar kind of thing, right? The source body capacitance and the drain body capacitance, we're going to talk about all of that kind of stuff when we're looking at things, but this to me makes a little bit more sense, especially with the naming convention of it being directly related to the terminals. So to understand where these guys come from, we are going to look at a cross section of a MOSFET during saturation operation. So bear with me a moment while I draw a giant picture. So here is our P-type substrate. Here's an N plus region that will be our source, but it could just as easily be our drain because of the way that these are constructed. This pink thing right here is polysilicon, or actually, no, this is my oxide layer, which realistically I should have drawn it in gray, but I didn't, so it is what it is. Okay, like so. All right. So let me define a couple of critical things here. So this is my overlap distance, and it is how far my gate oxide layer extends into the drain region and the source region. Typically small, but it is always going to be there, and it is required to be there because if not, we wouldn't be able to pull electrons around like we need to film our channel. Okay? Since we're looking at a device in saturation, I'm going to explicitly define my channel, and it's going to be pinched off like so. So we can see a few things here from the jump, okay? So we are going to have some capacitance between our gate and source caused by channel conversion. So that's typically going to be a pretty big thing, at least in comparison to all the others. This is our gate drain capacity. Typically going to be very small because there's not as much charge stored there. We are going to see a capacitance between the drain and the body because we have PN junction that is reverse biased. We are also going to see a capacitance between the source and the body because we have a PN junction that is reverse biased. And then just for the sake of argument, down here, let's pretend like my body terminal was on bottom and not an implant on top. Doesn't particularly matter. All right. So let's throw math at this. Okay. The gate source capacitance CGS arises because the polysilicon gate forms a parallel plate capacitor with the channel region COX. When the channel is tapered and pinched off, the gate capacitance is approximately 2/3 WL times COX. Additionally, the overlap of the gate over the source diffusion region yields a capacitance C overlap. And so what we find is that CGS is 2/3 WL times our oxide capacitance per unit area. So this is representing what's going on in the channel. This is just a simple approximation of, we have a parallel plate, or actually, we used to have a parallel plate capacitor. Now we have one plate that's parallel and one that's slightly askew. And if you were to literally break it down into differential elements and integrate as the distance between the plates becomes smaller and smaller and smaller from the source side to the drain side, it looks like approximately 2/3 of the area of the top plate times the generic capacitance COX. And then on top of that, we also have WL overlap times COX from the contribution of this region right here, where our overlap length is typically 1/20th to 1/10 of our actual channel length. So it just represents some fraction of the total channel length L. Our gate drain capacitance is just W times the length of the overlap times COX. Okay. Our source body capacitance, CSB naught over 1 plus VSB over V naught to the M. CDB is CDB naught over 1 plus VDB over that same V naught. Why is the built-in voltage in the source body capacitance and the drain body capacitance the same? Yeah, exactly right. So it's all about how the device is fabricated. And we know that our source implant and our drain implant are literally equally doped because they're formed at the exact same time with respect to our substrate doping. So they can't not have the same doping. 100% correct, Laura. Great job. All right. So not going to get too in the weeds here with regards to actually calculating these things, even for the BJTs. They're just going to be quantities that are given to you, but I want to talk about how these things are sized typically. Okay. So our gate source capacitance is usually larger than our source body capacitance, which is roughly the same as our drain body capacitance. It's not going to be exactly the same because typically VDB is actually going to be smaller because we apply a larger voltage at the drain than we do at the source for an NMOS transistor. And then below that, we are going to have our gate drain. So realistically, this guy is on the ballpark of 2 to 5 femtofarads. And all these are somewhere in the ballpark of 0.5 to 1 femtofarad, just depending on our conditions. So the capacitances for the MOSFETs, how do they compare to the capacitances that we talked about for our BJTs? Smaller, a lot smaller, about an order of magnitude smaller, I believe, right? So MOSFETs typically don't hit the high frequency regime until later than BJT-based devices because the internal capacitances are smaller. All right, so I've got some other business here about determining the unity gain frequency of a MOSFET transistor, but instead of deriving it, because we only have 4 minutes left, I'm literally just going to give it to you. So our unity gain frequency, omega t, just like it was for BJTs. So in a BJT, we saw that it was GM over the largest capacitance. It's the same thing. GM over CGS approximately. How could it happen? All right. So that's enough for today. So on Wednesday, we're going to get into kind of an overview of frequency response to transistor amplifiers, and then get into the nitty gritty stuff. Yes, I'm going to push back homework 4. Is that correct? Until tomorrow for sure. Problem 1 took me 10 minutes, maybe. Problem 2, drawing the small signal model. I want to talk to you, North, about it because I think we might have messed something up when we were talking about it.